Today we are going to discuss about the case study on material failure in aircraft components, right? Okay, so nowadays we have faced many problems like material failure, right? Okay, so why this material failure will be happened? So this is because of the defects present in that material, right? Okay, so what is meant by defect? Defect is nothing but the imperfections or irregularities of in the presence of atoms, right? Okay, we are well known about crystals, right? So what is meant by crystal? So the regular periodic arrangement of atoms, okay. So the regularity will be missed in this area, that's called defects, okay. The imperfections or irregularities are called as defects, right. So we have many defects, okay. So point defect, line defect, and plane defect, and then volume defect. We have many defects, okay. So point defect is the one-dimensional defect. So line is the two-dimensional defect. Plane is the three-dimensional defect. So in three-dimensional defect in aircraft components, the material failure happens due to the presence of grain boundaries. Okay, so grain boundary is the planar defect. Okay, so this is the three-dimensional defect. It happens due to the irregularity of atoms in the two components. Right. So let us consider the two lattices. It will join together. So in this joining area, there is a mismatching of atoms. These happens. That's called a grain boundary. Okay. So let's please explain the case study of today's case.
Our case study, material failures in aircraft compounds. The aircraft turbine blades often experience the high stress and temperature. Investigation revealed that the grain boundaries, imperfection, and uniform crystal structure contribute the permanent failure. There are three steps. First step is analyzing how the crystal imperfection could lead to the stress failures in high stress
okay, so today our case is material problems in the aircraft components, right? So mainly we have the three case studies, three questions here. So please explain the three questions.
First questions, analyzing how the crystal imperfection could lead to such failures in high stress aerospace application. Okay. Second is recommend the stable crystal structure for treatment to enhance the strength and the lifespan of a turbine attachment. Third is purpose of a method to control the crystal growth during the manufacturing of minimizing grain boundaries.
Okay, so next.
The main aim of this topic is determining and the understanding of crystal imperfection in highly stressed aerospace components.
Okay.
Nowadays we facing the challenges on operating environment in aircraft due to imperfections of crystal like temperature, stress level, rotation. In temperature, if it exceeds 1400 degrees Celsius, it may increase the possibility of grain boundaries. In stress level, centrifugal forces and thermal cycle, rotation speeds up to 15,000 RPM. It may also affect. It results in the failure of premature component and design.
Okay, very good. This is the main area we focusing here. Okay, so what's the problem is that so it will while heating the temperature is very high, right? So 1400 degrees Celsius. So while increasing the temperature, while increasing the temperature up to 1400 degrees Celsius, then sudden cooling it creates the grain boundaries. Okay, so grain boundary is nothing but grains is nothing but the smaller particles. Okay, so it will produce the particles. So grains. Okay, due to the presence of grains, it will affect the elasticity of that material. So it also will create the defects, right? So the high temperature and high pressure application will produce the defects, right? Okay, next.
Failure mechanism to find the specific reason which caused failure from the input. Failure mechanism analysis is temperature, thermal stress and accumulation. Grains boundaries exhibit a lower melting point, creating weak zone during thermal cycle. Crack initialization, stress concentration at grain boundaries, and imperfection forming microcracks. Inner granular propagation, cracks travel along grains boundaries and the path of least resistance. Catastrophic failure, rapid cracks growth leads to the blade fracture under operational loads.
Okay, good. Next.
Why grain boundaries matter? Structural vulnerability, atomic mismatch zones, higher diffusion rates, preferential oxidation sites, reduced grip resistance. Why grain boundaries matter? Structural vulnerability, atomic.
Hey.
Why grain boundaries matter? Structural vulnerability, atomic mismatch zones, higher diffusion rates, preferential oxidation sites, reduced grip, resistance, corrosion, successfully.
Okay, good. Next.
The primary recommended crystal structure for avoiding those crystal imperfections are single crystal turbine blades and nickel based superalloys. Those crystals helps on eliminating the grain boundaries entirely.
Okay, good. Okay, next.
Advanced heat treatment protocols. Solution heat transmitter, rapid cooling, annealing, primary and aging, secondary aging.
So as I discussed earlier, so I said that while increasing the temperature up to high temperature and sudden cooling is called rapid cooling. So it will produce the grains. Okay, so in the presence of grains will reduce the mechanical and electrical and thermal properties of the material. So this is the main problem faced here. Okay. Okay, next.
Crystal growth control methods. Bridgman technique. Process
Okay.
control directional solid heat 3 to 6 millimeter per minute with precise temperature gradient. Result is the grain.
So to avoid the grain boundaries, right?
Single crystal growth with seed results.
Okay, good. Okay, so done. Okay, so the nowadays, so how to reduce the grain boundaries? So what we have to do is nothing but we have followed the mechanism. Okay, so crystal growth mechanism. So how to apply crystal growth mechanism? So by using the growth mechanism, right? So what is it? Mechanism is Bridgman method. Okay, Bridgman method. We have used Bridgman method. It will reduce the presence of defects, right? It will reduce the grain boundary defects. Okay, so we have used advanced techniques, growing method. So we have reduced the defects, right? So these are the case study we discussed here. Okay, so our case study is why mechanical failure happens in the aircraft components, right? So due to the grain boundaries present in the crystal, it will failure the mechanical properties of aircraft components, right? Thank you all.
Thank you.